Thank you, everybody. My name is Zerihun Assefa from North Carolina A&T State University. I'm an organic chemist. I'm gonna do a lot of structural show. Unfortunately, Carmen, I'm sorry I did it with not Regapo, but with Broker. So, but you gonna promise me to use we try to change, yeah. Okay, these are my topics. I'm gonna discuss coordinating transition metals with lanthanide and actinide through various polymers, the ligands that would form some coordinating polymeric features. I'm gonna have a structure with extended linear and zigzag chains, rings and hollow channel features, and some of our compounds also show high stacking with very unusual spectroscopic behavior. I don't know whether I can discuss that part, but depending on how the chairperson would allow me, I will try to go as fast as possible. So the first target would be structural features of metallic ions of lanthanide and group 10 and 11 metal ions, transition metal ions, which are bridged by cyano-ligands, where the cyano-ligands are used as a bridging ligands. But I'm going to also show you various other coordinating ligands that would show interesting structural features. For a very long time, this platinum tetracyano complex is known to have a linear metal-metal interaction. The platinum tetracyanides are columnar in structure, and what was studied for a long time was that the platinum-platinum distance ranges from 3 angstrom to up to 3.7 angstrom, and that distance would vary depending on several factors. And one of the interesting features was that the spectroscopic property would have a tunable properties. And this tunability will be attained by various chemical variation, including as simple as varying counter ions, temperature, pressure, and external magnetic fields. So you can change this platinum distance by using these parameters, and some of this temperature, pressure, etc. I'm not gonna talk, but the structural features that we use by varying chemical variation is what will be the focus of my talk. So the first aspect is using a counter ion. This has been studied a while ago. Counter cation, for example, if you use the potassium, sodium, platinum tetracyanide, if you change it to thallium, then the thallium-platinum interaction will remove the columnar behavior. This columnar feature is destroyed if you have a thallium introduced there, because the thallium ion will interact with the platinum and remove that one. So the columnar feature is known long time ago. So it knows that some counter cations will destroy this columnar feature. But in our case, I'm going to show you that when we use, instead of thallium, when we use various lanthanide ions, then a coordination polymeric feature would also be produced, and not the columnar feature, but the coordination polymeric feature will be exhibited. For example, changing the columnar coordination polymeric with lanthanide 3. For example, if you have a residuum ion and interact with platinum tetracyanide, then there will be a coordination of the platinum tetracyanide on the lanthanide ion here, and the interaction would be in a trans feature, a platinum tetracyanide trans feature, and you're gonna see this is the asymmetric unit of this feature, and there will be another platinum tetracyanide in the center, forming a ring system like this one. So you're gonna have a trans interaction all along, but the europium, the praseodymium, and the platinum tetracyanide would form this type of two-dimensional ring system is also possible. If we take, for example, instead of if we introduce a ligand like terpyridine in this case, then this was some structural feature. We did a lot of structural feature by using terpyridine in the system, and the motivation was that we can coordinate to lanthanides because of the active nitrogen side. We can coordinate to the lanthanide ions, and the more focus here was technically, although I'm a structural work, I'm also spectroscopic work. I've conducted a lot of my work is energy transfer from donor to lanthanides, and so this was one of the motivation I had to introduce this terpyridine. And we did this type of feature. So if we can coordinate the lanthanides with the terpyridine and also with the platinum tetracyanide, and we induce energy transfer from this platinum tetracyanide donor as well as from the terpyridine ligand, and pumping the lanthanide accordingly, and then can we enhance the emission that would come from the lanthanide system with the motivation we have in this work. And so we're starting with europium nitrate. This was the structure we found. And sure enough, we can coordinate the platinum tetracyanide to the nitrogen atom of the cyanide, and the 3 nitrogen atoms of the terpyridine also coordinate. And the nitrate ion, also a bidentate ligand, also one of the nitrate ions also coordinates directly to the europium ion, and there are 2 water molecules, this oxygen 4 and 5 are water molecules. And this synthesis was done in acetonitrine, so that's why you have a free acetonitrine ligand here. So this is the feature, but if we do the structural work, what we see is that the coordination environment exhibits first the cyanide, that the platinum tetracyanide is coordinated in a cis fashion, and 2 europium sites are coordinating, so it forms a zigzag type chain in the feature exhibited is a zigzag chain of metal ions that consists of a cis interactive platinum tetracyanide and the terpyridine ligand, and so that coordination in a zigzag chain is observed when we use the europium nitrate. The anion was acting and nitrate, but simply changing the anion. Then what we have done a lot of it, but I'll just give you some examples. The counter anion in this case was changed to a non-coordinating. Instead of the nitrate ion, we use a triplet system, a europium triplet system, which is a non-coordinating ligand. Then we were able to change the structural feature from zigzag chain into, this is a zigzag chain that we can find, where the platinum tetracyanide is coordinating in a cis fashion. And this zigzag chain is in addition to that, another platinum tetracyanide coordinates in a trans fashion and forming a ring system here. So we can form a ring system consisting of the metal ions. So instead of the zigzag chain is converted to a metal ion, and simply because of the avoidance of the interacting of the interference of the other ligand, that is the triplet is no more coordinated in this case. So the interesting feature is that you get a hollow feature. The crystal structure shows that this system shows a Holo feature itself is another story, but I'm just showed here. Again, if we change from a non-coordinating ligand from the triplet to an acetate ion, which is similar to a nitrate ion, then obviously the oxygen, which is the hard ligand, can coordinate with the europium ion. And what happens is that the platinum tetracyanide is kicked out of the coordination environment. And in that case, there is no more europium tetracyanide platinum interaction exists, and the structure shows as mononuclear europium system, and the platinum tetracyanide is just act as a counter anion, and it's no more coordinating in the inner sphere. And so we just varied in this case the story that I want to interact or convey here is that we just changed the anion and we were able to see various interesting structural features here. But at the same time, the consequence of this variation on the photoluminescence behavior was also very, very interesting for us. In that, normally in these complexes, the lanthanide ion exhibits a very strong emission, and both the terpinidine and the tetracyanoplatinate act as donors, as originally predicted. But that donation, the behavior or the way the donor system donates the excited state energy transfer is exhibited is different or influenced by the structure, and so the structure influences the donor's ability. For example, the zigzag chain that I discussed earlier does show an excitation spectrum when it is monitored at the europium D0F2 transition line. We see the sharp FF transitions from the europium excitation, but also we see a very huge broad emission excitation band, which is not characteristics of europium, but it clearly indicates that it corresponds to the donor system. So the donor system provides a strong excitation, energy transfer, and so the emission behavior clearly shows only emission originating from the europium system. So sharp emissions were observed in this case. Unlike other systems, this is again the same thing. We have a terpinidine TCP absorption region in this broad emission, but these sharp lines are the excitation bands for the europium FF transition. That's characteristics of lanthanide FF transitions are normally sharp emissions, and the emission is like this one, but this is a direct evidence that energy transfer takes place from the donor system to the europium lanthanide system. So this is typical because, for example, the tetracyanoplatinate, in the absence of energy transfer, does emit in the 520 nanometer region, or depending on the type of cation. For example, if you take gadolinium, gadolinium has a very large clock, and so energy transfer is not possible from platinum tetracyanide, or lanthanum is another one that doesn't show any energy transfer. In that case, the emission that is characteristics of the platinum tetracyanide is exhibited in the visible, close to the visible region, and so which is not observed in the europium system. On the other hand, what we observed was that when the europium acetate anion, when the platinum tetracyanide was kicked out of the coordination environment, does show emissions that correspond to the platinum tetracyanide. Clearly, again, indicating that for energy transfer to take place, a coordination is a requirement. Otherwise, the two ions show their own independent emission behavior. So this is again the same, the acetate anion. The acetate coordination with the platinum tetracyanide is out of sphere coordination, is kicked out in the system. So we do see a broad emission that corresponds to the platinum tetracyanide, as well as a weaker emission corresponding from the europium ion. Further structural modification was done by using gold and silver dicyanides, in addition to the platinum tetracyanide. This is also clearly important for us because gold and silver dicyanides are small molecules, and therefore their coordination is sterically unencumbered, linear features, and so they can readily coordinate, just like the platinum tetracyanide, the gold dicyanide can coordinate through the cyanide ligand, and so it can be inserted into the transition into the lanthanide system. So, in addition to that, gold and silver are known to show orophilic and argentophilic interaction, where the metal-metal interactions are known to be exhibited in these features, and the metal-metal interactions are sources of low energy luminescence in other systems as exhibited. So in our case, we decided to add group 11 and group 2 cyano complexes, the platinum and the gold and silver dicyanides, into the europium system in this fashion. So we took this one and we reacted with gold dicyanide, and this is the structure we observed. Sure enough, the gold dicyanide, this is the gold dicyanide interacting. If you take this one, two gold dicyanides, the platinum tetracyanide interacts, as well as gold dicyanide also is in coordinating with the terbium system in this case, and the terpyridine system is also coordinating. But what is interesting is that the alignment of the platinum, the alignment of the platinum and the gold system here. So we do see a platinum, gold, gold, platinum system showing a tetrameric cluster here consisting of gold atoms and platinum atoms aligned in this fashion. The distance is 3.199. The platinum gold, whereas the gold distance is 3.312. This is known to be in the coordination geometry. Most of gold interactions, the distance between gold is about, ranges from 2.6 all the way to 3.5, and so they're clearly indicating that there is a metal-metal interaction in this case also. There's another feature of this one. There's two gold atoms are interacting here, but also another platinum interaction is also involved, whereas the other platinum tetracyanides are also involved. So the structure is a little bit messy, but I just pulled out the gold and the platinum cases here, showing instead of the tetrameric and hexameric clusters are also observable in this feature. And when we take out the platinum tetracyanide and only use the gold dicyanide, this is what we get. In this case, these are the gold dicyanide. Again, two gold dicyanide are interactive, but a third gold dicyanide is aligned in between the two atoms because of the metal-metal interaction that's exhibiting distance of 3.32 angstrom. And the gold-gold bond is around 125, 124.9. So these are the features. There's no polymeric feature, but the gold atoms are coordinating together. Also, they do show interesting spectroscopic behavior. Another structural feature that we were able to observe was we took, instead of the europium, we took the gadolinium in this case and reacted it with gold cyanide, and the reaction of lanthanide 3 nitrate with terpyridine and potassium dicyanurate provides dimeric urophilic interaction, and this is the structure. No more polymeric feature is observed, but we observe a dimeric feature here, where the gold cyanide interacts with another gold cyanide with the neighboring atom with the 3.51 angstrom. One of this feature, structurally probably is just a dimeric feature, but very interesting feature was that the alignment of the terpyridines are interacting as a 5' interaction here observed. That's how the terpyridine ligands are observed. And this observation was provided a very interesting, it took us probably over a year or so in order to understand the system, because this system provides a very huge red emission, and red emission from gadolinium is not observable. Gold, the gold could be, but that requires a very short gold-gold distance in order to get a red emission. And we finally found that the high interaction in this system forms excellent feature, and that excellent feature was the source of that emission. We published that one in organic chemistry a few years ago. So this is the story. The chairperson has time's up notice, so I'm going to stop here. Thank you.